Here we go. All right, so we're going to get started on the next section, which is chapter 6, which is heat. Okay. We started the chapter looking at just different concepts of heat, of course, solids, liquids, gases, conduction, convection, and radiation. You already know all that stuff, so I'm not going to go through all that. Okay. We're going to take a look at the physics of it. Okay, so the first thing that we did in terms of calculating how much heat there is in an object, what do we do? What do we decide? What's the formula for it? Okay, so Q equals to mc delta T. Okay, of course, M was mass, C is your specific heat capacity, and your temperature, T is your change in temperature. Now, when I was marking your quizzes and your tests, a lot of people just didn't understand this delta T. Okay, so when we're talking about delta T, what are we talking about? Change in temperature. Yes, so delta T, of course, is change in temperature, which is TF minus TI. And there were easy questions I gave you on the quizzes and the tests, and I had people calculating the one part of it, but not the second part of it. If you're going to do that, you have to calculate this, and you got to calculate that and subtract the two. Or you just subtract the two and calculate the change in the specific heat capacity. Okay, so this is calculating heat. Okay, in terms of course, what's this measured in? It's not measured in joules. It's not measured in, what is it measured in? Okay, oh goodness. So yes, as we were saying, it's measured in joules. Oh. Okay, so when we're talking about the specific heat capacity right here, we're talking about an object gaining heat or losing heat. For example, when we talked about your water going from a certain temperature to another temperature. Okay, now what state are we talking about here? Do they tell us what state this is? It doesn't matter? Does it matter? You don't think it matters? It matters? So okay, so it does matter. The state of the object does matter. So we're looking at each state will have a different specific heat capacity. By state meaning solid, liquid, or gas. Okay, so each state will have a different C for the object. For example, the C for water, which is liquid, is not the same. Is how much was it again? 4180 joules per kilogram degrees Celsius. Then the C for ice, which is a solid state, something totally different. And then the C for vapor, water vapor, which is a gaseous state or gaseous state, something totally different as well. So you have to be careful when we're looking at this as to what state it is in. Okay, for most states I've given you the specific heat capacity, and just make sure you are aware of that. Okay, so we started with this first. Are we good with this? Can I erase this? Okay, the next thing that we did after this is what? Well, not latent, we did something else before that. Q lost and Q gain. Okay, so just like the law of thermodynamics and the law of conservation of energy, same thing here as well. Energy cannot be created or destroyed. So just because an object has or gains heat, it has to lose heat from somewhere else. So my thing that we did was Q lost plus Q gained equals to 0. Okay, and then we started with mc delta T plus mc delta T, which equals to 0. Now I actually want to do a question for this one because this is more confusing than it looks, right? So mc TF minus TI plus mc TF minus TI, which equals to 0. An example, so I'm going to use the old textbook. You have one? Is this this is the Q loss plus Q gain one? No, this is different. This is not it. You have to use a different one. I'm just going to use this from here, okay? Okay. So the question is as follows. This is page 152 in the old physics Nelson textbook. Okay. Old text. Okay. And the question is as follows. It says a 200 gram piece of iron. So mass of iron is 200 grams. Of course, convert this into kilograms. Simple mistakes again. Okay. At 300, so Ti of the iron is 350 degrees Celsius. Okay. Is submerged in 300 grams of water. So mass of water is 300 grams, which is 0.2 kg. Okay. Thank you. Thank you for reminding me. Okay. All right. So we're going to do the loss from the iron plus a gain from the water, which will give you 0. Now remember, we're taking the iron and we're putting it inside water. So we're going to have an iron-water mixture, okay, with a final temperature that's for both. The iron and the water will both have the same temperature. So we'll start with this first, which is 0.2 times 450, okay, times TF, which we don't know. We don't know the combination of the two, minus 350. Okay, plus 0.3 times 4180 times, we don't know the combination there, minus the original temperature of the water was 10 degrees Celsius. Okay, so what do you get when you do 0.2 times 450? 0.2 times 450. 90. So 90 TF minus 350 plus this one right here, 0.3 times 4180. 1254 TF minus 10, okay, which equals to 0. Now we're going to expand it. Okay, we're going to expand it. So it's going to be 90 TF minus 90 times 350. 31,500 plus 1254 TF minus 12540, which equals to 0. Get all the like terms, so 90 TF plus 1254 TF minus 1250 minus 31,500, which equals to 0. Bring it all on the other side. What does the TF add up to? 1344 TF, correct? Which equals to, what's 3150, 12540? What do you get? 44,040. Okay, your TF, of course, is 44,040 divided by 1344. And what is your TF? So the 33 degrees. By the way, this is the same question I gave you on the quiz. Yeah, it's exactly the same question. It is. Yeah, that I gave you before. So 33 degrees Celsius. Both of them combined together to give you a final temperature of 33 degrees Celsius. This is what Q loss and Q gained is. Okay? All right, are we good with this? Okay, so we're going to erase this and continue with the next thing. Yeah, so heating, cooling curves. Okay? Okay, so the next thing that we're going to take a look at, of course, is heating, cooling curves. Okay. All right, so heating, cooling curves, basically what we're saying is when you have an object that is being heated through all its different stages, this is what it might look like. So there's your temperature, and there's your time or energy, okay, or energy, whatever you want to call it. More energy needed as we go further and further up. So this is when it's in solid state, solid. This is when it's in its liquid state. and this is when it's in its gaseous state or vapor state. Okay, so imagine if we're doing this for water. Okay, so of course this is 0 degrees Celsius, and right here it's 100 degrees Celsius. Okay, so this is your solid state right here. So what we say is we're going to start out with the first one, which is Q here, which equals to mc delta T. Remember the change in temperature from whatever temperature it was to 0 degrees while it's in a solid state. We got to make sure you do the C of ice here. Okay. This right here is the extra energy needed for you to break the bonds that are between the solid particles so that it becomes a liquid. And this right here is known as, okay, so it's QF, which equals to MLF. M, of course, is your mass, and LF is your latent heat of fusion. Now that, of course, is also a value that is given to you. So every object has a different heat of fusion. Okay, so this is your second Q right here, Q2. The Q3 right here, of course, is again going to be mc delta T. Okay, here, this is going to be the specific heat capacity of water. Okay, again, you're going to take a look at it from 0 degrees to 100 degrees. A certain amount of energy is needed. Then we got to that stage where the water particles are going to get broken down, the bonds are going to get broken down to make it into a vapor. And this right here is another energy, which is QV, which equals to MLV. And this right here is latent heat of vaporization. Okay, vaporization. So this is going to be your Q4. And the last, of course, is Q5. Again, mc delta T. But your C here is for vapor. So this is how you would take a look at or calculate heating, cooling curves as you go from one state to another state. Please make sure that you are adding. So if I was to ask you a question where I say, what's the total energy required to go from a particular temperature to a particular temperature, you are taking all of these into account. In this situation, it would be Q1 plus QF plus Q3 plus QV plus Q4, or Q5 I should say. And that whole total will be the total energy needed for you to be able to break down an object that is a solid and make it into a vapor. Okay, this is heating, cooling curves. Is there anything else that we did in this chapter besides this? I mean, we did renewable, non-renewable resources and all that stuff. So, but you just read over that section, is not a big deal. Anything else that we looked at but I didn't talk about here? Yeah, so if not necessarily subtract. We're going to be adding this way, right? So if I say how much heat was lost, I'm still adding, right? Yes. And then you would have a total energy. So I would go this way starting from here, and I would have a loss of whatever amount of energy was lost as an object went from a vapor into a solid. Cool? Any questions, concerns? Yes. Will be given, yes. Okay, yes. That's correct. So as an object goes from a solid to a vapor, you're adding energy to break the bonds. As an object goes from a vapor to a solid, you're taking away energy or releasing energy. Okay? All right. Thank you very much.